Yeah, welcome to this lesson. This is going to be our last uh, concepts to cover in unsupervised learning in classical ML. So, we're going to be covering something called principal component analysis (PCA), and it's a decomposition technique. In the last class, we looked into um, um, we looked into DB scan. But in this class, we're going to be looking at PCA. And what's PCA? So PCA is actually a decomposition technique that helps us to reduce uh, our data set to a number of principal components. That is, let's say you have let's say you have like 20, 30 features, 10 features. You want to features, by features I mean columns, and you want to reduce it to a particular number of columns. Let's say something like um 3, 4, 2. The way to do that without losing any real information, the way to do that is by using PCA. It's by doing PCA. Now, so it means PCA is a decomposition technique. Sorry, I'm trying to set up the board. Right, so we are here now. So how does PCA work? So majority of the time, whenever you are working on projects, either supervised learning or unsupervised learning projects, you are usually going to have to reduce a lot of correlated data columns, reduce it down to a particular number of uncorrelated features. And the idea is, why take all of these 30 columns when we can just shrink them down to like 3, 4 columns? And it is particularly interesting in um something like clustering. Because whenever you do clustering, you want to see how the cluster has happened, let's say on a three-dimensional chart. And that's just the highest that you can go. You cannot go 4 dimension and plot that kind of chart. So in that kind of situation, PCA can help you. You firstly, you know, decompose all of the features that you have into, you know, 3 columns, and then you can now visualize that. But generally, PCA helps us to handle having to work with very, very large number of correlated columns, right? So let's look at what are the steps of PCA. So the first thing is, okay, let's look at this practice data set. So we can say X. I say we have another column called Y, another column called Z. So this is going to involve like a lot of calculation. I'm not going to be doing them by hand because it's going to like waste a lot of time. Like I'm going to just go over it like we did with DB scan, right? So just show you a few things, then the formula and the idea behind it. So let's say we have, I don't know, maybe 2, 3, 4, 4, 5, 6, then maybe 5, 6, 7. This data set that we have. So if we want to, let's say we want to decompose this to 2 columns, for example. So we want to decompose it to 2 columns. So we are saying number of components is going to be 2. So the first step, step 1, is always to choose the number of components. Choose number of components. Number of components. Yeah. So a number of components is the number of columns that you want to reduce to. So you want to reduce all these 3 columns to 2 columns at the end of the day. So what's step 2? Step 2 is actually a very, very important step. So step 2 is to standardize our data set. So we standardize our data set by computing the z-score of each column, which is what standard scalar does for you. So that's going to be x minus mu all over standard deviation. So for each of the columns, for this column, this one, and this one, we are going to scale them in a way that we take, let's say this is 2 plus 3, 5, 9, 9 divided by 3, 3. So we go 2 minus 3, that is going to be minus 1 divided by whatever standard deviation that is. So we use it to get scaling. And the reason why this is extremely important is because of the next step after this, which is step 3. Step 3 is that in step 3, we want to compute the covariance matrix of the scaled data set. So we want to compute the covariance matrix of the scaled data set, and that is why we need step 2. We don't want to compute the covariance matrix of the original data set. Why is that? Because the covariance of the original data set is something like this. You can see covariance of x comma y. Let's say that's what we are looking at for x comma y. The normal formula, the standard formula is going to be summation of x minus mu of x, or some people will say x bar, I guess. Then y minus mu of y. Now, all over n, actually, all over the number of stops that you have. So in this case, if you do this, right, it is just a lengthy process of doing x minus the mean of all of the x's. And the problem that we can have is if we have very large values, like we have really, really large values, they can kind of like contribute unfair um, um, variation to the covariance that we are computing. So if we don't standardize, we are encouraging unequal contribution of each principal component. So what does that mean? It means that if we actually scale it down, scaling something down means that your data set is now going to be uh, between 0 and 1. So your data set is going to have mean of 0 and standard deviation of 1. When you scale it, then after scaling, your whole data set is expected to have, each column your data set is expected to have mean of 0 and standard deviation of 1, variance of 1. So it means all of these guys are now going to be 0. Mean of x is going to be 0, mu of y is going to be 0. So basically, that is going to leave your covariance of x comma y as summation of x, y all over n, basically. So because this is now 0 and this is now also 0. So that is the reason why we need to do scaling as our step 2. So after that, step 3 is we compute covariance. I am assuming you know what covariance means. So covariance is basically how two variables vary together, how they move together, how they associate together. That is covariance. Now, and we need to see it for each of the columns we compute for covariance of xy, covariance of x on x, covariance of y on x, covariance of y on z, like that, like that. So once we get our covariance, the next thing that we're going to do, which is going to be step 4, is going to be to compute. Step 4 is going to be to compute the eigenvalues and eigenvectors of the covariance matrix. So basically, what does that mean? So the idea is that if you do not really understand what eigenvalue and eigenvector means, you probably should watch some other dedicated video. But I'm just going to try to explain it as best as I can. So basically, if you have a matrix A, let's say A is equal to something like 2, 1, 3, 4. This is a matrix. So the general idea is that a particular vector exists, and we call it eigenvector, that if we multiply it, let's call it x. So we are calling this eigenvector x. If we multiply this particular vector by A, it is not going to change the direction of A. It is only going to either expand it, squish it, or turn it to the negative axis. So that is ladder x like this. So the idea is that if we take that particular eigenvector, multiply it with our original matrix A, what we are going to get is something that either expands or shrinks the original matrix that we are working with. So it means that we still tend to like retain the information in our original data set, right? What has just happened is that we've shrunk it down, or in some cases we've expanded it. So that's basically what eigenvector do. And eigenvalue is actually the degree to which the eigenvector scales or shrinks something. And if you have negative, it means that we are moving it to the other side, like um we are turning it all the way to the other side, like deflecting it to the other side. But there are a lot of explanations in between that, but that is just like the real thing. So what we do is we compute eigenvalue and eigenvector of each of the covariance matrix that we have, and you start off. If you understand how to do eigenvalue and eigenvector, you are not going to be doing it by yourself. Though it has been done for you. But if you must know, to actually solve for this ladder, for example, if what we are doing is this particular A. So to get the eigenvalues of this particular A, what we are going to do is we are going to say we are going to solve a characteristics equation. So we're going to say something like A minus lambda I, if I'm still correct. Determinant of that is going to be equals to 0. So the solution of this equation, this characteristic equation, is going to be what gives us our lambda I. So to translate this to something that we have here, it's going to be equals to 2 1 minus lambda. No, that is wrong. That is wrong. That's going to be 2 minus lambda 1, then 3 4 minus lambda, and that's going to be equals to 0. And it's not even going to be this kind of bracket. It's going to be straight bracket like this. So we just compute the determinant of this. So I'm not going to be doing that, but just to show you, then minus, that's how you compute determinant of a 2 by 2 matrix. Minus, this is 3 here, so 3 times 1 3 minus 3. So the solution of this equation here is also going to give you lambda 1 and lambda 2. Then that's what you're going to use to compute your eigenvector and all of that, and you're going to have the values that you need. So after getting your eigenvectors, now your eigenvectors are the principal components. The eigenvectors are the principal components, and what you want to do is that's step 5. Step 5, you're going to sort the eigenvectors in descending order of eigenvalues, like how big the eigenvalues are. That's what we are going to use to sort the eigenvectors. And don't forget, we've chosen our number of components earlier as 2. So what we're now going to do is we're going to choose the top 2, because we say n components is 2. So we're going to choose top 2 eigenvectors, and then proceed to the last step, which is step 6. We now project that. So we project the chosen eigenvectors on the scaled. We're going to be doing that on excuse me, on the scaled data set. So, and how do we do that? We are going to, it's just this, is that's our way of getting the final decomposed data. So the final decomposed data is just going to be x underscore scaled multiplied by, let's say, w, and w is basically the vector containing the principal component. So if we multiply them together, this is dot. If we multiply them together, what we are now going to have is the new two columns that's going to contain information that all of these three columns contains approximately without us needing to use all of the three columns. So that's basically how principal component analysis works. It is an extensive calculation, but it is something that you probably can find that you will definitely, not probably, you definitely find it online, but it requires that you probably, if majority of the things here sounds alien, you probably firstly want to understand how standard scaling works. It's simple: x minus mu all over standard deviation, and it reduces our mean to it makes our data set have a mean of 0, standard deviation of 1. Then you also understand how to compute covariance matrix. This is the formula for doing that. Just even understand the whole idea of covariance to begin with. Then next one is eigenvalue and eigenvectors. And it's a bit handy, but it's really simple to understand. And that is that. So let's go use PCA. So I'm going to say from, let's connect that, say from scikit-learn dot decomposition import PCA. So like I always say, we are not really ever going to, so we can say import. We are not really going to be doing all of these things with our hand, but it is just really important that we understand what is happening under the hood. I'm going to say import pandas as PD. I don't know if we are going to need numpy, but still we import it. And from sklearn, we need that stuff for scaling. Import standard scaler. I think that's everything. We might also need label encoder because we are going to be working with different data sets that is going to px.data.tips. So we are going to be using this tips data set, and we are going to try and decompose it. So it's coming up, and it is up. And we have our data, all of this data. We are going to just shrink the whole thing. So how do we do that? The first thing to do is we convert all of this um, textual data, these categorical variables, convert them to numeric. So how do we do that? We're going to say encoder equals label encoder. Then we can say data. Then we can get all of our columns, cat underscore code. So we don't even need to do that. I just say for columns, column in data dot select the types include, and we are only including, what are we including? We are including object. We are saying dot columns. Let's print out column first and see if it gets the right ones. Yeah, it got the right one. So we can just go ahead and encode and say data of column equals encoder dot fit transform encoder dot fit transform data column. So if we check our data.add now, everything is perfect and cool. Yeah. So the next thing, all of these things, they are all encoded. The next one I want to now do is scale. Don't forget step 2 here says that we must, step 3, no, step 2, we must scale our data set. So how do we do that? We use standard scaler. So we say scalar equals standard, hold on, standard Perfect. So we can do column underscore names. It's going to be equals to data dot columns. Phew. So we can go and say data equals scalar dot fit transform data, and we can go and say data equals pd dot data frame, and data is going to be equals to data, just to convert it back to a pandas data frame, column underscore names. So we can check data dot add to see that our scaling is done. Right, so our scaling is done. All of the data set has been scaled. Now the next thing to do is now perform PCA. When you say perform PCA, so we're going to take all of these columns and shrink it down to 3. So I'm going to say n component equals 3. So I'm going to say, you can call it model if you want. Model equals PCA, and number of components equals number of components. So we also need to set random state. So we're going to set random state equals 3, and that's all. So the next thing I want to do is we want to set column names. So we can say column underscore names. It's going to be equals to, since we have 3 columns, we're going to say column 1, column 2, and column 3. Then we can come here and say data equals model dot fit transform data. Then we can pass that back into a data frame, the pd.data frame, and that is going to be data equals data, columns equals column names. Then we can do data.add to check out. So see if that works. Yeah, it worked. So we've taken all of this data here, we've shrunk it down to these 3 columns, and approximately all of the information in this particular 7-column data has all been shrunk down into these 3 columns. So yeah, that is how we do PCA, and we can now take this and do whatever it is we want with it. Do clustering, do DB scan, do some supervised learning, whatever thing that we want to do. So yeah, that is how we do PCA, and yeah, see you in the next one.